everyone, this is Babitha, working as Assistant Professor in the Department of EC in Institute of Aeronautical Engineering. In this session, I am going to discuss about differential amplifier. While coming to the contents, just I'll revise what is meant by amplifier and what is the function of the amplifier circuit, and then I'll go with the differential amplifier and what are the different types of differential amplifiers are there. So before going to the differential amplifier, first of all, we have to know what is the basic function of the basic amplifier. So the function of the amplifier here is to amplify the applied input signal. So amplification is nothing but here it will improve the strength of the signal, or else we can say it will improve the amplitude of the applied input signal. So for that purpose, we can utilize either bipolar junction transistor or field effect transistor or else operational amplifier for the amplification purpose. So for this particular amplifier designed by any type of device will perform the amplification of the applied input signal, and it will provide the improved magnitude or amplitude of the signal. So in order to make it as, for example, transistor as an amplifier, first of all, we have to operate the transistor is in the active region. So as we know, transistor is a 3-terminal device with the base, collector and emitter terminals. So in order to operate it in active region, we have to make base emitter junction as forward biased and collector to base junction as reverse bias to make it as active region of operation. And along with this, we need to provide the proper DC voltages as well as stabilization required to get the faithful amplification. So how we can get the faithful amplification here? So whenever we fix the proper operating point Q of that particular amplifier, so that we can able to achieve the maximum amplification from the amplifier circuit. But how we can achieve this proper operating point means by providing the different biasing techniques. By using different biasing techniques for the transistor, we can able to achieve the proper operating point. So to make the highest amplification or high amplitude signal from the amplifier, we have to make the operating point in the middle of the active region, not in the cutoff region or not in the saturation region. So to make it is in the active region, we have to find the ICQ value as well as VCEQ value in the active region. So in these two values, VCEQ is directly proportional to what is the DC voltage we are providing for the transistor. So it will not vary here. This value is fixed. But the value of collector current is varying due to different parameters here. This may be vary due to the current amplification factor, or this may be vary due to the temperature variations, or this may be vary due to the applied input voltage for the amplifier. So because of all these reasons, this collector current is varying. So to make it a stable or constant value, we have to maintain proper current gain as well as temperature values for the amplifier circuit, so that we can able to maintain the proper operating point in the active region, so that we can able to get the faithful amplification from the amplifier circuit. And along with this, we have to provide the proper stabilization circuit for the amplifier to make it a stable operating point. So this is about the normal amplifier circuit. This one we already discussed. So while coming to the differential amplifier, so the name itself indicating it will amplify the difference of the applied two input signals. That is nothing but in the case of differential amplifier, we are going to provide the two input signals for the amplifier. So to design this type of differential amplifier, we require two identical transistors. In the case of normal amplifier, we are utilizing the single transistor, But to design the differential amplifier, we require two transistors to get the two input signals and to achieve the difference of the two input signal amplification. So I have already mentioned to design this we require two identical transistors. Those are Q1 and Q2 we are taking here. Okay, and along with these two identical transistors, the resistances of the transistors are also should be equal to design this differential amplifier. So here we are taking two transistors Q1 and Q2. If we take the emitter resistances of the two transistors, those are RE1 and RE2, those should be also equal here. And also the collector resistance of two transistors, those are RC1 and RC2, also must be equal here. And the magnitude of the supply voltage VCC must be equal to the magnitude of the emitter voltage minus VE. So these voltages we should measure with respect to ground here. So to design any differential amplifier, we have to follow these three conditions. All the emitter and collector resistances must be equal and the applied voltage polarities also equal. So for that purpose, I am taking two transistors here, two identical transistors. Okay. And here I am taking the common emitter transistors. Both are common emitter transistors. So this is the Q1 transistor and this one is the Q2 transistor. And the RC1, the collector resistance of the first resistance is RC1 and the collector resistance of the second transistor is RC2. So those are equal. And similarly, the emitter resistance of the first transistor is RE1 and the emitter resistance of the second transistor is RU2. Those should be also equal here. And the VCC voltage as well as VE voltage values are also equal here. So that we can say these two transistors are having identical characteristics. So these particular transistors we can utilize to design the differential amplifier circuit. So this is the differential amplifier circuit. How we are making this circuit means we have already considered two identical transistors. So the collectors of the two transistors we are connecting together here, and also the emitters of the two transistors also we are connecting together here. In the previous slide I have shown these two are the two identical transistors or two identical amplifiers we can say, and we are interconnecting the two transistors to make it as a differential amplifier. And for the two transistors we are providing two voltages, two input voltages, that is V1 for the Q1 transistor and V2 for the Q2 transistors. And these resistances RS1 and RS2 are the source resistances in order to provide the voltage for the base of the two transistors. And the function of the collector resistances is used to measure the output voltage of these two transistors. And we have already mentioned the emitter resistances of both the transistors are equal. So that's why I have made it as RE1 is equal to RE2 is equal to RE. I replaced it with a single resistance RE. So here two voltages, supply voltages VCC and VE are connected common here because those two voltages are supply voltages are same here. And the two emitter terminals also we are connected it as parallel combination of RE1 and RU2 and replaced it with a single resistance RE. And the two input signals V1 and V2 are applied to the base of two transistors Q1 and Q2. And the output voltage we are taking between two collectors here. The output voltage we are measuring common between two collector terminals here. Okay, and the collector resistances are also equal, so that's why we can replace it with RC1 is equal to RC2 is equal to RC. So in the ideal case, the output voltage must be 0 when we are providing two input voltages are equal. That is in the ideal case. But in the practical case, we may not provide both the voltages are equal. One is greater or one is less. For example, if I am making my input voltage V1 as greater than V2. So in that case, the output voltage polarity is depends upon the polarity of the first input, that is V1. If V1 is positive, we will get the output voltage as positive. If V1 is negative, we will get the output voltage as negative. Or else, if I take my input voltage V1 is less than V2. So in this case, we will get the output voltage has the opposite polarity of the applied input voltage. Why? Because the applied input voltage is less than the next voltage, that is second voltage. So always the polarity of the output voltages depends upon the which type of voltage we are providing to the two bases of the transistor. That is depends upon the positive or negative and depends upon the values of the V1 and V2. So this is about the differential amplifier. So the basic function of this differential amplifier here it is 2. It will take the difference of two applied input voltages and it will amplify the difference of the two input voltages. So the output voltage V0 is gain times the difference of two input voltages here. In the case of a normal transistor, we will get V0 equal to A times the applied input voltage. But here we are taking, instead of single voltage, we are taking two voltages, that is from two transistors. So depends upon the different configurations used in the differential amplifier. These are divided into 4 types. That first one is dual input balanced output differential amplifier. Dual input balanced output differential amplifier is nothing but it is going to use two inputs, V1 as well as V2. So while coming to the output, balanced output is nothing but the output we will measure between the common point of two collectors of two transistors, that is across C1 and C2, collector terminal of first transistor and the collector terminal of second transistor. Between RC1 and RC2 we will measure the output voltage so that we can say it as the balanced output. And we are providing the two inputs, so that's why it is dual input. So that we can call it as dual input balanced output differential amplifier. For this amplifier, we are providing the two inputs and we are taking the common output. And the next one is dual input unbalanced output differential amplifier. So in this case also, though it is dual input, we are taking two inputs, V1 and V2. But the output we will measure either at collector terminal of the first transistor or else the collector terminal of the second transistor. So that's why we can call it as unbalanced differential amplifier. In the previous case, we are taking the output at the common point of two collector terminals of the transistor, but in this case we are taking either at RC1 or at RC2, so that's why it is unbalanced differential amplifier. So that's why it is called as dual input unbalanced output differential amplifier. And the third one is single input balanced output differential amplifier. That is nothing but in this case we will provide the input for either V1 or V2 only, that is at the base of the Q1 transistor or to the base of the Q2 transistor, or not at the same time. So any one of the input we are providing here, so that's why it is called as single input. So while coming to the output we are taking again the common point between the collector of the first transistor and the collector of the second transistor, so that's why it is again balanced output. So that's why overall we can say it has the single input balanced output differential amplifier. And the last one is single input unbalanced output differential amplifier. So in this case also the input voltage we will provide either V1 or V2. So that's why single input. But the output also we will measure across either RC1 or RC2 of the two transistors. So that's why it is unbalanced differential amplifier. So depends upon the number of inputs applied and at what point we are measuring the output. These four types of differential amplifiers are classified. So now we will see the circuits of the four differential amplifiers here. So in that first one is dual input balanced output differential amplifier. To design that particular amplifier, in short we can call it as DIBO amplifier. Okay, so to design this we require two identical transistors Q1 and Q2 with the two equal collector resistances as well as two equal emitter resistances. Here we may take any type of differential amplifier. These conditions are must. Collector resistances must be equal, emitter resistances must be equal, and the characteristics of both the transistors must be ideal here. So here dual input, so that's why we are providing both the inputs V1 and V2 for the basis of both the Q1 and Q2 transistors. And the output voltage we are taking across the collectors of two transistors in common. So that's why balanced output. If we are measuring across two common points, so that we can call it as the balanced one. If we are taking any one collector means so that it is the unbalanced. So this is the dual input balanced output differential amplifier, and for both the collectors we are providing the common supply VCC voltage, and both the emitters resistances are replied with the common resistance RE, and that is connected to minus V. And next circuit is the dual input unbalanced output differential amplifier. So in this case also again Q1, Q2 are identical, and RC1 and RC2 are also equal, and RE1 and RE2 are also equal, so that we replaced it with the emitter resistance RE. So here again it is dual input, so that's why we are providing both the voltages V1 and V2, and the output we are taking across the Q2 transistor collector terminal here. That is across RC2 we are measuring the output voltage, or else we can also measure across the RC1 here, any one terminal only. So that's why we can call it as the unbalanced output differential amplifier. In short we can call it as DIUO amplifier. And the third type of amplifier is the single input balanced output. So here it is single input, so that's why we are providing the input voltage for the base of the first transistor, and the second transistor base is grounded here. Why? Because we are not at all providing any input to this particular transistor. And balanced output means the common point of both the collector terminals we have to measure the voltage V0. So in short we can call it as SIBO, single input balanced output differential amplifier. And in the last differential amplifier is the single input unbalanced output. So in this case also single input, so that's why we are providing the input for the first transistor, and the base of the second transistor is grounded here, and the output we are measuring across the collector of the second transistor, not at the common point of two collector terminals of the transistor. So that's why it is the unbalanced output. So in short we can call it as SIUO amplifier. Okay, these are the four different configurations of the differential amp. So actually why we are moving for this differential amplifier even though we are having the amplifier circuit. So in the case of single stage amplifier designed with the single transistor, it can able to amplify the signal, but it may not reach the proper voltage gain and proper current gain, and it may not provide the required input impedance as well as required output impedance. So in order to improve all these parameters of the single stage amplifier, we are moving for the differential amplifier here. So if we interconnect a more number of differential amplifier stages, so that we can able to get the much amount of gain here. So gain factor may be increased here. Okay, and the basic advantage of direct coupling of the differential amplifier means it will remove the lower cutoff frequency imposed by the coupling capacitors. So instead of directly connect the one stage with another stage, if you use the coupling capacitors, here we may get the problem of lower cutoff frequency. So that's why in order to avoid that, directly we are connecting the output of one stage to the input of the next stage, so that it can able to amplify both the DC as well as AC input signals. Why? Because we are not including any capacitors. If we include the capacitor, means it allows only AC signals and it blocks the DC signals. So that's why in that because of that reason also we are not including any capacitors for the cascading purpose here. So now we'll see the analysis of the dual input balanced output differential amplifier. So for that purpose, again I consider the dual input balanced output differential amplifier. Just now we have discussed about this particular circuit. Both the transistors Q1, Q2 are equal, and for that amplifier we are providing the two input voltages V1 and V2 to the two bases of transistors Q1 and Q2. So the output voltage also we are measuring between the two collectors C1 and C2, and which are at the same DC potentials. That is nothing but for both the collector terminals of the transistors we are providing the common supply, so that we can say both are at same DC potentials. So in this we are going to do the DC analysis as well as AC analysis in order to find the different parameters of the amplifier. So in the case of DC analysis, we are going to calculate the operating point required for this particular differential amplifier. So to obtain the operating point, that is collector current and collector to emitter voltage for differential amplifier, we have to go with the DC equivalent circuit. So how we can get this DC equivalent circuit means, to get the DC equivalent circuit, we have to short both the voltages V1 and V2 are grounded here. Okay, both the input voltages for the transistors V1, V2, we make it as ground or zero potential. So to do the DC analysis, see that the internal resistances of the two input terminals or two input signals are denoted by source resistance Rs here. Why? Because the source resistance values, all the resistance values are equal here. So the Rs1 is equal to Rs2. So that's why we are replacing it with the Rs resistance. And next, and both the emitter biased sections of the differential amplifier are symmetrical in all the respects. So therefore, here we are going to find the operating point for only one transistor instead of two transistors. Why? Because all the characteristics are same here. So if you find for one transistor, that is also same for the second transistor. And the same values of ICQ and VCU can be used for the second transistor Q2 here. And to find the ICQ as well as VCEQ values, here I am applying the Kirchhoff's voltage law to the base to emitter loop of the transistor Q1. Here we are applying the KVL. So if we apply the KVL to this, what we will get? So the drop across this resistance is, so we have already replaced Rs1 is equal to Rs2 is equal to Rs. So that's why instead of Rs1, I am taking Rs directly here. So Rs into IB, that is the first term, and plus base to emitter voltage VBE, plus 2IE here, 2IE into RE. Why we are taking here it as 2 times IE into RE means 1 IE RE from the transistor Q1 and 1 more IE into RE from the Q2 transistor. Both are run with the same emitter resistance. So that's why the current flowing is also same in the both the resistances. So that's why we are taking here it as 2IE is equal to VEE. But the base current IB is equal to IE by beta DC. That is, from the beta, we can write this. Okay, beta equal to IE by IB here. So that's why we can write it as IB equal to IE by beta DC. And here always the collector current is almost equal to the emitter current. Why? Because the drop across the base is very, very less, or else IB current is very, very less. So that's why we are approximating the collector current is equal to the emitter current. So the emitter current is equal to the collector current, that is equal to VEE minus VBE. From this first equation, we can write VEE minus VBE divided by this one 2RE plus RS by beta DC. Okay, so this one I am considering it as the first equation 1. So in the case of silicon transistors, base to emitter voltage is 0.6 volts, and in the case of germanium transistor, VBE voltage is 0.2 volts. And generally this RS by beta DC term is very, very less compared to the 2RE value, so that we can neglect this RS by beta DC value. Why we are getting this value is very less means the value of beta is very high, but it is present in the denominator. So the overall value of RS by beta DC will be very less compared to the 2 times RE resistance. So that's why we are neglecting this particular term. So the emitter current is equal to the collector current, and that must be equal to the VEE minus VBE divided by 2RE. So this is the collector current ICQ value. This is the one of the coordinate of the operating point Q. And to find the VC voltage, and again we are taking the emitter current in Q1 as well as Q2 are independent of the collector resistance RC. So the value of RE sets up the emitter current in transistors Q1 and Q2. So for the given value of VE supply, so the voltage at the emitter of Q1 is approximately equal to the minus VBE if the voltage drop across this RS resistance is negligible. So in that case, we have already calculated the value of collector resistance, so that we can able to find the collector voltage VC, that is given by, again if you apply the KVL to this loop. So that is VC, we can write it as VCC minus the drop across the collector resistance is ICRC. So VC is equal to VC minus V. So the value of VC we have calculated, that is VCC minus ICRC minus V is nothing but drop across base emitter junction, that is VB. So VC equal to VCC plus VB minus ICRC. So this is the value of VCEQ. So this is the second coordinate of the operating point. We have calculated ICQ value as well as VCEQ value. So by using these two values, we can able to find the operating point of this dual input balanced output differential amplifier. So this ICQ and VCQ values are applicable for all the types of differential amplifier, all the 4 types of differential amplifiers. So from the DC analysis, we have calculated the operating point, and next we are moving for the AC analysis. So in the case of AC analysis, from the circuit we can say we are applying 2 inputs V1 and V2 for the 2 bases of the transistors Q1 and Q2. So the output voltage we are measuring between the 2 collectors RC1 and RC2, and which are at the same DC potentials here. So DC analysis has been done to obtain the operating point of the 2 transistors. And similarly, to find the differential gain AD as well as input impedance and output impedance, we have to move with the AC analysis. So to do the AC analysis, we have to get the AC equivalent circuit. So how we will get this AC equivalent circuit? Means by replacing this differential amplifier with the R parameter model. Okay, and these DC voltages, this VCC as well as VCE, VE must be 0 for the AC analysis. So after replacing the two transistors with the R parameter model, so this is the equivalent circuit, and this is for the transistor Q1 and this is for the transistor Q2. Two are the two R parameter equivalent values. See here. Here two DC emitter currents are equal. So therefore the resistances RE1 dash as well as RE2 dash are also equal. So we can replace that RE1 dash as well as RE2 dash is equal to RE dash here. So this voltage across each collector resistance is 180 degrees out of phase with respect to the input voltages V1 and V2. This is same as in the case of CE configuration. See here, the polarities of both the output voltages are shown in the figure here. So the collector C2 is assumed as more positive compared to the C1 here, even though both are running through the negative with respect to the ground here. And if we apply the KVL to the loop 1, this is the loop 1 and this is the loop 2, what we will get here it as the voltage we are applying is V1, so that's why V1. So the drop across RS1 is RS1 into IB1 plus the drop across emitter resistance is IE1 into RE dash plus this RE drop is IE1 plus IE2 into RE. So the same equation we'll get from the loop 2 also, but instead of first transistor polarities, we are getting the second transistor polarities here. Why? Because V2 equal to RS2 IB2 plus IE2 RE dash plus IE1 plus IE2 into R. And now if we substitute the current relations in these two equations, what we will get? The base current is equal to emitter current by current amplification factor beta, this one we know already. So if you substitute these two values in this equation, and also the input voltage V1 is equal to, if we substitute this value in the first equation, we will get it as RS1 by beta into IE1, and the remaining total equation is as it is. And similarly in the second equation also, if we replace IB2 with IE2 by beta, we will get it as V2 equal to RS2 by beta into IE2, and the remaining equation is as it is. And again we are assuming this RS1 by beta as well as RS2 by beta are very small compared to the RE as well as RE dash here. Okay, this value as well as these values are very high compared to this particular value here. So that we can neglect these two terms here. So after neglecting the two terms, we will get it as RE dash plus RE into IE1 plus RE IE2 equal to V1 from the first equation, and similarly from the second equation we will get this. And if we solve these two equations V1, V2 to find the emitter currents IE1 and IE2, we will get it as these two. After simplifying these two equations, or after solving these two equations, we will get two emitter currents IE1 and IE2, and these must be equal to the collector currents of first transistor as well as the second transistor. And the output voltage is the differential voltage here. Why? Because we are using the two transistors Q1 and Q2, and VC2 is the voltage across the second transistor, and Vc1 is the output voltage across the first transistor. So the overall output voltage is the difference of the collector voltages of two transistors, Vc2 minus Vc1. And again Vc2 is nothing but drop across the collector resistances, that is minus Rc into Ic2 minus of minus Rc into Ic1. And if we take Rc common here, we will get it as Ic1 minus Ic2. And we can replace it with the IE1 minus IE2. Why we are replacing it with IE1 means IC is always equal to IE here. So that's why we are replacing the collector current with the emitter current in this equation. So the differential output voltage is this much. And now we have to substitute the values of IE1 and IE2 in this equation. So after substituting the IE1 and IE2, we will get it as this much. So the overall output voltage is RC by RE dash into V1 minus V2. So the differential amplifier will amplify the difference of two applied voltages V1 and V2 here. And the differential input signal is Vd here, that is equal to V1 minus V2, and that is the voltage gain of the dual input balanced output differential amplifier. So the voltage gain AD equal to Vc by Vd, that is common mode voltage by differential mode voltage. Common mode voltage is nothing but both the voltages we will apply as same. And the differential voltage means one voltage is less or greater than with respect to the other voltage. So if we maintain like this, the differential gain we will get it as Rc by Re dash from this equation 1. So this one we are taking it as the second equation, and this is the differential voltage gain we can achieve from the dual input balanced output differential amplifier. And next we need to find the how much input resistance we are getting from the differential amplifier. So what is the differential input resistance here? So it is defined as the equivalent resistance that is measured at the any input terminal, that is at Q1 transistor or at Q2 transistor. We can measure from the input terminals of the Q1 transistor or at the input terminals of the Q2 transistor. But while measuring at one particular transistor, the input for the other transistor should be grounded. So that is nothing but Ri1 is the input resistance seen from the Q1 transistor. And in that case, V2 must be 0. And similarly, if we set V1 is equal to 0 means we can able to measure Ra2 resistance from the second transistor. So the resistances Rs1 and Rs2 we are neglecting here. Why? Because those are very small compared to the input resistance of the transistors. So after neglecting the source resistance Rs1 and Rs2, the input resistance Ra1 is nothing but V1 by I1. What is the input voltage we are providing here? Okay, and the base resistance, the base current IB here. And in that case, V2 must be 0. And again, what is our IB1? That is IE1 by current amplification factor beta. So substitute that value here. And again, substituting the value of IE1, just now we have calculated the IE1 value, substitute that IE1 value here. And in this case, again, the RE resistance is very, very high compared to the RE dash resistance. So that we can write it as RE dash plus 2RE is far greater than 2RE. Or else RE dash plus RE is RE. Why? Because these two will get cancelled. So the input resistance Ra1 of this dual input balanced output differential amplifier is 2 times beta into Re dash. So this one we are taking it as the third equation. So till now we have calculated the operating point, that is ICQ and VCQ, and next the differential gain AD, and the third parameter we calculated here it as input impedance Ra1. Similarly, we can also calculate Ra2 from the second transistor. That is 2 times beta into Re dash. So the factor of 2, why we are getting here it as, because Re dash of each transistor is in series. So that's why Re beta Re dash plus beta Re dash. So that's why 2 beta Re dash here. So to get very high input impedance with this differential amplifier, we can utilize Darlington transistors instead of normal bipolar junction transistor, or else we can also utilize field effect transistors. And the next parameter is the output resistance. So output resistance is nothing but the equivalent resistance that we have to measure at the output terminals of the transistor. Those should be while other terminal should be grounded here. So therefore, the output resistance R01 measured between the first transistor collector, that is C1, and the ground is equal to that of the collector resistance RC here. So similarly, if you want to measure across the second transistors, in that case we can take it as R02 measured at collector of the second transistor C2 with respect to ground, equal to the collector resistance RC. So that directly we can write the output resistance across transistor Q1, that is R01, is equal to the transistor 2, that is R02, is approximately equal to the collector resistance RC, how much we are providing for the two transistors. So the current gain of the differential amplifier is generally not defined here, and in the case of common emitter amplifier, the differential amplifier is also a small signal amplifier. That is nothing but it can able to amplify the low frequency range of signals, not for the high frequency range of signals. And it is generally used for the voltage amplification and not for the current and power amplification because of the limitation of low frequency signals. It will take it as the input here. So this is about the dual input balanced output differential amplifier. And next we will see the second type of differential amplifier, that is dual input unbalanced output differential amplifier. Here the analysis, the DC analysis as well as AC analysis is same for all the four types of differential amplifier, but the values of the parameters will be changed. Why? Because sometimes we are not taking two inputs and sometimes we are not measuring the common output here. So because of the two reasons, the parameters may be varying here. So in this particular case, dual input unbalanced output case, we are providing the two inputs, but we are taking the output across only single transistor, that may be at a Q1 collector or at Q2 collector. So in here we are providing the two signals V1 and V2, and the output we are taking across the collector of the second transistor, that is at C2. And the output is referred to as unbalanced output because the collector at which the output is measured is at some finite DC potential with respect to ground here. Okay, so here there is some DC voltage at the output terminals without any input signal is applied. So that's why the DC analysis is same as the first case. Why? Because in the first case also we have taken two inputs, V1 and V2. So that's why both the ICQ as well as VCQ values are as it is. Just now we have calculated these two values from the dual input balanced output differential amplifier. The two values are same for this dual input unbalanced differential amplifier also. So that's why directly I am moving for the AC analysis. So to do the AC analysis, I have already mentioned we have to nullify or ground the DC voltages, and I am replacing this differential amplifier with the AC equivalent circuit. And to find the differential voltage gain, we have to apply the KVL for the two loops, 1 and 2 loops. That is, if we take the first loop, from the first loop, we will get the equation as the input voltage PE1, and the drop across the Rn resistance is Re1 into Ib1 minus the emitter resistance drop is Re into Ie1 minus Re into Ie1 plus Ie2 equal to 0. Take it as the first equation. And similarly, if we apply the KVL for the second loop, we will get the same equation but in terms of subscript 2 here. So these two equations are same here. So that's why IE1 and IE2 will be also same here. So that's why both IE1, IE2 from this 1 and 2 equations, we will get it as same. And the output voltage V0 is equal to VC2 we are taking. Why? Because we are measuring the output across the second collector here. So that's why we are taking the output V0 equal to VC2, that is minus RC into IC2, or else we can also write it as minus RC into IE2. Why? Because collector current is equal to the emitter current I. So here if we substitute the value of IE2, this IE2 value if you substitute in this V0 equation, in the fifth equation, we will get it as this much. And in this case also, this emitter resistance is very high compared to Re. So this particular term we can replace it with only Re. And here we can replace it with 2Re. So after substituting these two conditions in this equation, we will get the output voltage V0 equal to this much, RC into V in1 minus V in2 divided by 2Re. And again this V in1 minus V in2 is nothing but the differential input voltage. So I can write this one as V0 is equal to RC into VID divided by 2Re. So from this, if I write V0 by VID is equal to RC by 2Re here. So in the case of previous balanced output differential amplifier, it is 2 times R beta into Re somewhat we got. But here RC by 2Re. Why? Because here it is unbalanced output. That is nothing but we are taking the output across single collector, not at between two collectors. So that's why it is becoming off here. Okay, so since at the output is a DC error voltage here, so therefore in order to reduce the voltage to 0, this configuration is normally followed by a level translator circuit in order to overcome that reduction in the gain. And the input resistance. So the only difference between all the circuits is in what way the output voltage we are measuring. The input resistance is seen from either input sources, does not depending upon any output terminal or any output voltage. So that's why the input resistance is same as dual input balanced output differential amplifier only, that is 2 into beta times Re here. And the output resistance we are measuring across the collector C2 with respect to the ground, and that is approximately equal to the RC. So the output resistance value is RC here. So in this session we have discussed about what is meant by a differential amplifier and how we construct the differential amplifier and what is the operation of the differential amplifier and what are the different types of differential amplifiers are there. And also we have seen the DC as well as AC analysis of first two type of differential amplifiers, and the same analysis is applicable for the remaining two types of differential amplifier. The thing is the parameter values may vary due to the application of different dual or single input voltages, and the output we are measuring at a common of both the collectors or at single collector. Only the two parameters they vary here. By considering the two assumptions into consideration, the values may be varying remaining two configuration, that is a single input balanced output differential amplifier and single input unbalanced output differential amplifier. But the analysis part is same compared to the remaining two types of differential amplifiers. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.